Hello everyone, in this video I will present my digital signal processing assignment. The objective is to analyze a noisy signal using FFT, design a digital filter, and evaluate the results in both time domain and the frequency domain using MATLAB. The goal is to reduce the noise while preserving the original desired signal. Let's go! For task 1, I generate a clean signal and a noisy signal in the time domain. The clean signal is a 10 Hz sine wave. The noise is a 25 Hz sine wave with a smaller amplitude. By adding them together, I obtain the noisy signal. The top plot shows the clean 10 Hz signal, and the bottom plot shows the noisy signal containing both 10 Hz and 25 Hz component. This represents the signal condition before filtering. Time domain plot shows the waveform distortion caused by the noise, but they do not clearly tell us the noise frequency. Therefore, FFT is used the next step to identify the frequency components. Next, I analyze the noisy signal in the frequency domain using FFT. From the FFT magnitude plot, two domain frequency components are observed. The main desired signal appears at approximately 10 Hz, and an additional peak appears around 25 Hz, which corresponds to the noise component. FFT separates the signal based on frequency, allowing us to choose a suitable cutoff frequency to preserve the desired 10 Hz signal while removing the 25 Hz noise. Based on the FFT, I designed a low-pass FIR filter. The cutoff frequency is selected at 15 Hz so that the 10 Hz desired signal passes through, while the 25 Hz noise is attenuated. The filter order is set to 100 to achieve a sharper transition band. FIR filters are chosen because they are stable and can provide linear phase characteristics which help preserve waveform shape. The pole 0 plot confirms the stability of the FIR filter. The frequency response confirms that frequency below cutoff are passed with minimal attenuation, while frequencies above the cutoff are significantly reduced. This indicates that the design filter meets the objective of suppressing the 25 Hz noise. The magnitude response shows attenuation behavior, and the phase response reflects the linear phase property of the FIR filter. The impulse response of the filter is shown here. The impulse response is symmetric, which is a key characteristic of a linear phase FIR filter. Linear phase filtering is important because it reduces phase distortion and preserves the shape of the original signal. Next, the noisy signal is filtered using field function. This performs the zero phase filtering, which removes phase distortion and keeps the filtered output aligned with the original clean signal. This is useful for offline analysis because it avoids the delay that usually appears in causal filtering. This figure shows the final time domain comparison. The noisy signal is shown in gray, the clean reference signal is in green, and the filtered output is shown as a blue dashed line. The filtered signal closely follows the clean signal and shows significantly reduced noise. This demonstrates that the filter successfully removed noise while maintaining the original waveform shape. In the frequency domain FFT comparison, the noisy spectrum contains a strong component at 25 Hz. After filtering, this 25 Hz noise component is greatly reduced, while the 10 Hz desired component remains. This confirms that the filter performs selective frequency attenuation as intended. The frequency domain result validates the filter design and the confirmation the improvement more clearly than the time domain observation alone. So, in conclusion, FFT analysis was used to identify the noise in the signal. A low-pass FIR filter was designed and applied to reduce the noise. The final results show that the noise is successfully removed, while the desired signal is preserved. This completes the assignment. That's all for me. Thank you for watching.